afternoon, guys. Now for the rest of this part of series resonance circuit. Look, the last rest of this part was where the 3 dB point. We're talking about the selectivity. What is the selectivity? And the relation between selectivity and the bandwidth. The selectivity of a resonating circuit is defined by the ratio of F naught and to the bandwidth of the circuit. So we can write that the selectivity of a resonating circuit defined by the ratio of F naught to the bandwidth of the circuit. Okay, so selectivity is F0 by F2 and F1. This is the bandwidth. So we can write this is the actually Q factor. So F1 and F2 are also called 3 dB point as the current ratio of I1 and I0. So 3 dB means dB ratio. It means that is 20 log 10 base I1 by I0. Or we can say that is 20 log 10 base 1 by root 2. Okay, because as the I1 is 1 by root 2 into I0. So I0 is cut down. And actually 3 dB is this dB ratio that is called -3. So I1 is lower than the I0. I1 is lower than this I0 by 3 dB, and similarly F1 is also lower than the F0 by the 3 dB. Okay, and now coming to the point of power dissipation. Next point, the power dissipation at the F1 and F2 would be the half of that of the power dissipation at the F0. Okay, and the effect of resistance on the frequency response curve. Look, effect of the resistance of frequency division curve is just like this. This is the smaller R, and this is the larger R. Okay, so you can see for the smaller R, this is the smaller R. oscillating, but the larger circuit is just going to the damped and it's achieves the stability as well as. Okay. So this is all about your series resonance condition, and now we are talking about parallel resonance. We're talking about parallel resonance or resonance in parallel circuit. Okay. So this is the R, this is the L, and then the C. So this is V, means sinusoidal wave. It is a AC, or sometimes it is given as the source voltage, and the current is going that is I. This I is the RMS current, and this V is the RMS V. Okay, and the current flowing through the resistance, this current was divided in three parts. So this current is flowing in the IR, current flowing in the inductance, that is called IL, current flowing through the capacitance, that is called the IC, the capacitive current, and the impedance is R, that is normal, and this is XL and this is XC. This is the impedance. Okay, so at the resonant condition, we can say that the XL must be XC. You know already that is XL equal to, when XL became XC, then this is called the resonant circuit. And what is the properties or what is the behavior of the resonant circuit? For this parallel resonant circuit, you know that is at it's look, when this is a resonant circuit, the circuit became a purely resistive circuit. So whenever the resistive circuit is there, you know there is a current and voltage are in the phase. So this is the I and this is the V. Okay. And what is the another factor is impedance is maximum and the current is, as the resistance is greater, so impedance is Z became the purely R, and impedance is maximum, then what happens? Current also the minimum, because if there is a resistance is high, then it will goes to the current become going to the downward. So write down this property, because all this time it was asked in as a short question. So at resonance condition, uh, as the XL equal to XC, because this portion will be going to the zero, so only R is remaining. So you can write the voltage and current in the phase. This situation, voltage and current in phase. Okay, as the as the circuit became purely resistive. Okay, and the impedance is maximum. Just remember these things in your mind because all short notes are coming this type of thing. Current is minimum because if impedance is high, current must be low. So now we are going for the graph for the impedance versus frequency graph. What happens? The impedance versus frequency graph. You can see if this is a impedance, this is Z, and frequency, or it is called, you can say omega. So you can see if this is a resonance frequency, this is omega r, this is the resonance frequency. Okay, then you can see this is the graph. Okay, so this is the maximum Z maximum. This is the Z maximum equal to R. Z maximum equal to R over there. Okay, you can see this is the impedance versus frequency graph. Look, at this resonant frequency, omega r impedance is maximum, but whenever you are moving towards any direction, either in this direction or in this direction, impedance is going to reduced. Okay, so at the resonant frequency, impedance is maximum, but as we move from the omega r or the resonance frequency, then it is reducing. This is the fact happening in the parallel resonance conditions. So we can write this. We can write this maximum. Okay, but moves from omega r in any direction impedance is reducing. Okay, so omega at the zero, omega at the zero, xl is zero. Okay, because omega into L, xl equal to omega into L, and omega at the infinity, then xc will be zero, as this is the omega c. Okay, it is infinity too, so this is a zero. So this is the properties of parallel resonance. And now we are talking about the another curve, that is current versus frequency curve. Look, this is the current versus frequency curve. That is I, and that is omega. Now, if this is a resonant frequency, then we can find this is if this is a current versus okay. So you can see at the resonant frequency, I is minimum. So whatever we have just told, this is the fact. Through this graph, we can observe this. So at resonant frequency, current is minimum. Current is minimum. And as we move away from the both direction, the current will be maximum. The current will be increasing. If if we move, then it will go to the higher position. So from this graph, could you remember one thing? So it looked like say band reject or stop band filter. It looks like a band reject or band stop filter. So parallel RLC circuit is a band reject circuit or band stop filter, looks like a band stop filter, and series resonance circuit looks like a pass band filter. Okay, so that's why this is called rejector circuit. That's why this is called rejector circuit. And parallel series RLC circuit is called the selector circuit because it is passes the particular band. Okay, just remember this thing. Another thing that is this RLC circuit, parallel RLC circuit is called the tank circuit. It is called the tank circuit. Tank circuit. Why this is called tank circuit? Why this is called tank circuit? Because in this, you can see if this is inductance and this is capacitance, then inductance stores its energy in the magnetic field. Inductance, this is capacitance. It stores sorry, I have to complete this circuit, otherwise it stores energy in magnetic field. And it stored its energy in electrical field or electrostatic field. You can say this electrostatic field. It is stores energy in electric field. So at the resonance circuit, what happens? It's working just like a volleyball. Means whenever it stores its energy, then it's discharges its energy, and whenever it discharges its energy, a capacitor stores its energy. So energy is if this is the energy, one time it is going here, one time going here. So it is ultimately accumulating over here, but it is moving from inductor to capacitor, capacitor to inductor, and it is going on. So that's why this circuit is called the tank circuit, and it is the behavior of this tank circuit. So you can just write down these things. the storage energy or the store energy is transferred back and forth between the capacitor and and coil and vice versa. Okay, the circuit is said to be resonant condition when the susceptance, this is called susceptance, okay. So this is the parallel RLC circuit and its properties. And now we are talking about mathematical expression of the parallel RLC circuit. No, this R is I is sorry, this is I. This I is the I RMS value, and the V is the actually V RMS value. Okay, so we can write from the above circuit. Just remember the circuit. This is resistance, this is inductance, and this is capacitance. Okay, and this is the source. So R, L, and C. You can see the I current is flowing over I R is flowing over there, I L is flowing over there, and I C is flowing over there, and total current is I. So we can write down that is I equal to I R plus I L plus I C. Okay. Or we can see going to the next. We can see as I equal to I R plus I L plus I C. We can write down that is V by R plus, what is this? This is V, this is V by X L, V by X C. Okay. So in this case, we can write down that is taking the V as a common, that is 1 by R plus 1 by J omega L plus J omega C. Okay. Now we can write down that V equal to 1 by R plus, we can take common, that is omega C minus omega L. Okay, because J is multiplied over here, so this is minus 1 and this J was going out. So we can take, you can see this portion is inverse of impedance. So this is called admittance. So this is called admittance. So this is also given in the form of Y, because this is a look like say admittance. So I is the V into Y, and for the resonant condition, this is the minimum. Okay, at the RLC parallel, at RLC. Okay, and have you any question up to that? Otherwise, please join for the next video.